Hi, folks. Today we're going to talk about the trigonometric functions. There is a lot to talk about with trigonometry. And so, what is trigonometry? Trigonometry is the study of a set of functions which derive their values from geometry as opposed to algebra. And so, instead of being related to the standard binary operations, they are related to the angles of triangles and circles. These functions complete the necessary set of functions to do meaningful work in calculus. There are two different approaches to introducing the trigonometric functions. So classically, we use right triangles to describe the functions in a Euclidean geometry plane. But in modern times, and by modern I mean the last 500 years, we use positions on the unit circle in a Cartesian coordinate system to describe the functions. And so let's see if we can gain an appreciation for these functions. Now, for this lecture series, there's an assumption you have Algebra 2. There is no assumption that you've seen trigonometry before. And so you can think of this as being a crash course in trigonometry. If you want to go more in depth, you should really take a trigonometry course. And so let's start with the idea of right triangle trigonometry, SOHCAHTOA. And so to begin with, we have angles in degrees. And so an angle is a measure of the spread of two line segments, or rays, which meet at an endpoint. Traditionally, we say that a right angle is 90 degrees and that there are 360 degrees in a revolution of a circle. We use 360 because it is divisible by a lot of things. In the case of a triangle, the sum of the interior angles of a triangle are always 180 degrees. Now, here we can see it written on a circle, and this is showing the degree measurement from the center as it goes out in the x direction to some other point on the circle. We are going to see this a lot. Which leads to the idea of angles in radians. And so there's a more mathematical approach to measuring angles, and that is using radians. And so suppose that you have a circle of radius 1. The radian measure is the arc length spanned by that angle. And so if we are saying that the distance from here to here is 1 unit, then the distance going around this arc would also be 1 unit. Sometimes we think of this in terms of the quotient of the distance traveled divided by the radius. If we're dealing with a circle of radius 1, we don't really have to worry about that. And so whatever this radius is, 1 radian would be the distance spanned going across this angle. And it's always going to be the same thing. It's always going to be that 1 radian is roughly equal to this. It turns out, because of how the circumference of a circle works, there are 2 pi radians in a circle. And so we would say the radian measure of 2 pi is equal to 360 degrees. A 90-degree angle would be pi over 2 radians. And the reason we care about radians is because we really need them to do calculus stuff. Note that this is where the idea of tau comes in. The idea that instead of using pi, it might make sense to instead use tau, because then we would say that the distance going around a circle would be just tau. It wouldn't be 2 pi or 2 tau. 1 tau would be 1 revolution. And so if you're going half a revolution, that would be a half of tau. We can fight about pi versus tau later, though. For our purposes, we're going to focus more on right triangles, at least to begin with. And so a right triangle is a triangle which has one angle which is right. And so one angle which is 90 degrees. If we select one of the other angles, then we can determine what the other sides are. We can give them names. And so if our angle is over here, the opposite side is the side which is opposite of the angle. The adjacent side is the side which is next to the angle and connects to the right angle. And then the hypotenuse, that's the term we use for the side which is always opposite the right angle. These 3 side names will be popping up throughout, and so it's good to get comfortable with them. Do note, if the angle had been up at the top, then the opposite would be down on the bottom, and the adjacent would be over here on the side. But the hypotenuse would still be opposite the right angle. Now let's remember something about similar triangles. And so if you have two right triangles, which have an additional common angle, then the two triangles are similar triangles. They're essentially the same, give or take scaling. If they have two angles in common, they have three angles in common. An important property of similar triangles is that their sides are always proportional. What this means is that if a right triangle has an angle theta, all other right triangles with that angle theta will have the same proportional side. And so in this case, we could say A to C divided by B to C is going to be the same as D to F divided by E to F. If we take the ratios of the opposite to the adjacent, it is always going to be the same as long as we're using the same angle. And so we're going to use these angles to define our new function. And so the trigonometric functions are determined by the ratios of the sides of a triangle. And so given some angle, the sine is the opposite divided by the hypotenuse. The cosine is given by the adjacent over the hypotenuse. The tangent is the opposite over the adjacent. Those are the three main ones. We do have three other ones, though. The cotangent is the adjacent over the opposite. The secant is the hypotenuse over the adjacent. And the cosecant is the hypotenuse divided by the opposite. Because of similar triangles, these ratios will be the same for any given angle, regardless of the size of the triangle. And so if you know what theta is, this ratio is guaranteed to be the same. And so let's consider an example. Here is our 30, 60, 90 right triangle. And so consider the equilateral triangle to the right, and we'll pretend this is an equilateral triangle. If we cut it in half, then we'll see that we get this new triangle. And this new triangle is going to have one angle of 30 degrees, one of 60 degrees, and one which is a right angle. Using the Pythagorean theorem, if the bottom side is 1, the hypotenuse is 2, and this left side is going to be the square root of 3. We can use this to figure out the trigonometric functions for both 30 degrees and 60 degrees. And so consider the triangle to the right. What would the values of sine, cosine, and tangent be for 60 degrees? If you want, give it a shot, see if you can figure it out. Here we go. And so in this case, for 60 degrees, the opposite side is square root of 3, the adjacent side is 1, and the hypotenuse is 2. And so the sine of 60 degrees is the opposite divided by the hypotenuse, which is square root of 3 over 2. The cosine is going to be the adjacent over the hypotenuse, which is 1/2. And the tangent is going to be the opposite over the adjacent, which is square root of 3. Oftentimes, to remember these, we use SOHCAHTOA. And so sine is equal to opposite over hypotenuse. Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Again, I don't know how I feel about mnemonics like that, but it gets the job done. So let's consider the exact same triangle. Can we do the same thing for 30 degrees? And if you'd like, pause the video, see if you can find sine, cosine, and tangent for 30 degrees. And we can. And so in this case, our opposite is 1, our adjacent is square root of 3, and our hypotenuse is 2. And so using the exact same formulas, we get the sine of 30 degrees is 1/2, the cosine of 30 degrees is root 3 over 2, and the tangent is 1 over root 3, which is also the same as root 3 over 3. Here's another example. This is the isosceles right triangle. And so what would the values of sine, cosine, and tangent be for a 45-degree angle? Well, we can calculate that without too much trouble. And so for a 45-degree angle, the opposite and adjacent are both 1, and then the hypotenuse would be the square root of 2. And so the sine and cosine are both going to be 1 over root 2, which we often rewrite as root 2 over 2, because you just want to rationalize it and make it so we can do math with it a little nicer. And then the tangent is the opposite over the adjacent, which is 1. And so with our right triangle trigonometry figured out for the most part, we can now move on to unit circle trigonometry. And so what's interesting is triangles and circles are basically the same thing. You might not believe me, but the formula is the same. And so when we consider a unit circle, it's a circle of radius 1. We call this the unit circle. The formula for it is x squared plus y squared equals 1. Note that this is just the Pythagorean theorem. A squared plus b squared equals c squared. Well, now instead of trying to figure out what this c squared term is, we're going to be setting c to be equal to 1, and that gives us the radius of a circle. So a point on this curve is given by x comma y. We can represent an angle from the origin in terms of the x-axis. And so that's what we saw before, where we say this right here is the x-axis. We'll let this be one part of the angle. Then the other part of the angle will just come out at whatever angle we need to deal with. Now, when we think of the unit circle, we can actually create right triangles on the interior of it. We know that the radius is 1, so each triangle will have x as the adjacent side and y as the opposite side. Using the triangles we've already played with, we can use similar triangles in order to figure out what the remaining sides are. And so remember before, we had dealt with a 45-degree angle, which is the same as a pi over 4 radian measure. Well, if we wanted to figure out what these two sides would be, we would end up getting root 2 over 2 and root 2 over 2. We can do this with 30 degrees and 60 degrees as well. And then using symmetry arguments, we can figure out what the points would be for all of the other values, all of the other angles in our unit circle. And so here are 16 different points on this unit circle, as well as the corresponding angles written in both degrees and in radians. Every trig student has to memorize this chart and be able to use it. And so it's important to know this if you're going to be going down a STEM pathway. Now here's the magic of the unit circle. For any angle, we can create a right triangle through a point on the unit circle. All of these right triangles have a hypotenuse of 1. And so if we are doing right triangle trig on these points on the unit circle, the sine is the opposite over the hypotenuse. Well, that's just the y value. The cosine would be the adjacent over the hypotenuse, which is just the x value. And so that means that every point on the unit circle corresponds to the cosine and the sine. We can use this to extend beyond what our normal right triangles might be able to handle. And so we'll be able to figure out the trigonometric values of any particular value. And so any angle, any radian measure, we can figure out what the corresponding trigonometric function is going to be. And we can just use this chart for the nice values. And so sine of 45 degrees, well, that's going to be root 2 over 2. The cosine, well, that's the x value at 45 degrees, which would be root 2 over 2. Sine of 5 pi over 6, well, what's the y value at an angle of 5 pi over 6? Well, here's 5 pi over 6, and the y value is 1/2. The cosine of 5 pi over 6, that's going to be a negative root 3 over 2. At 270 degrees, that's coming down here. Our sine is -1 and our cosine is 0. We can even go around an extra time. And so if we do 390 degrees, that would be a full revolution and then 30 degrees more. And so the sine is going to be, I don't know about that. Oh, did I make a typo here? Our sine of 390 degrees should be the 1/2. And our cosine of 390 degrees should be the root 3 over 2. Hate when I have typos like that. Yeah, the cosine is always going to correspond to the x value, and the sine is always going to correspond to the y value. So be careful of that. For the remaining trig functions, well, we can define them in terms of sine and cosine if we want to. We know tangent is sine over cosine. Cotangent would be cosine over sine. Secant is 1 over cosine, and cosecant is 1 over the secant. We can also define them in terms of x and y values, because remember, our sine and cosine are just y and x when we're talking about the unit circle. And so on the unit circle, we could say that the cosecant is 1 over y, the secant is 1 over x, our cotangent is x over y, and our tangent is y over x. Trigonometric identities. So now that we have the idea of unit circle trigonometry, we can start asking what types of properties are going to pop up. And so in trigonometry, we often utilize identities to manipulate expressions. We've already seen a few, which we use to define the trig functions, and we call these the quotient and reciprocal identities. And so tangent is sine over cosine, cotangent is cosine over sine. Then we have these three, which are the reciprocal identities. What's nice about these identities is it means we can always turn any trig function into sine and cosine. And so no matter what you got, it's really just a bunch of sines and cosines. We also have Pythagorean identities, and we've got 3 of them, but they all come from this idea. And so we know that this is a right triangle. We know this side is sine. We know this side is cosine, and we know this is always 1. Because of that, we know that sine squared plus cosine squared is equal to 1 squared. And so the Pythagorean identity in trigonometry is sine squared plus cosine squared of a given angle is always 1. Well, from this, what happens if we divide everything by sine squared? Or what happens if we divide everything by cosine squared? Well, dividing by sine squared or cosine squared is going to give us these other 2 identities. So tangent squared plus 1 is secant squared, or 1 plus cotangent squared is cosecant squared. These 3 are considered the Pythagorean identities. There are a lot of identities. So what happens if we are adding or subtracting 2 angles together? Can we figure out the trig values for that? We can, and we can prove them. And so these are things which have geometric proofs. We can determine what sine of a plus b is, what sine of a minus b is. Same with cosine, same with tangent. Well, what if we have a formula for adding 2 angles together? What if we double an angle? Can we double an angle? And what if instead of doubling an angle, we want a half an angle? Well, we have formulas for all of those. And so if we are doubling an angle, we can figure out a new expression to figure out what it is. If we're having an angle, we can do that as well. Another option is, what if we want to turn cosine into sine or sine into cosine? We have a way of doing that. What if we want to turn cotangent into tangent or tangent into cotangent? We can do that. Same with secant and cosecant. We can go back and forth between these functions whenever we want. Ultimately, there are a lot of trigonometric identities. These are all provable relations between the 6 trigonometric functions. And sometimes we use trigonometry, or sometimes we use geometry to prove them. Sometimes we use algebra to prove them. But these are some of the guiding properties that we can prove in trigonometry. And then we have to use them. And if you'd like, here's a sample problem. Prove that 2 tangent of theta secant of theta is equal to sine of 2 theta divided by cosine of theta times 1 minus sine squared of theta. This would be a standard problem in a trigonometry course. The way you would approach it is you have to basically create a string of equations where you just apply substitutions or other properties to try and simplify one side until you get to the other side. And so in this case, starting with the right side, sine of 2 theta over cosine of theta times 1 minus sine squared of theta. Well, we can rewrite the top using the double angle formula. We can then cancel the cosines. And then we can rewrite the 1 minus sine squared in terms of cosine squared. Breaking it apart, we will get a sine over cosine and a 1 minus cosine, which gives us the 2 tangent theta secant theta. And so this expression on the left and this expression on the right are the exact same thing. You do proofs like that a lot in trigonometry. You also sometimes have to solve equations. So this is an example of a quadratic form equation. 3 cosine of theta plus 3 equals 2 sine squared of theta. In order to solve this, what you would do is you would rewrite your sine squared in terms of cosine squared, because then we can get 2 cosine squared of theta plus 3 cosine theta plus 1 equals 0. We can factor this just like we would factor a polynomial. And then using the zero product property, either the first thing is equal to 0 or the second thing is equal to 0. And we can try and figure out when those are going to occur. Because of the fact that the angles are going to repeat every 2 pi or every 360 degrees, we end up getting that there's an infinite number of answers. And we can figure out exactly where all of those infinite answers are. So now on to graphs, on to the analytic geometry of the trigonometry. And so when we're thinking about graphing trig functions, there's a few things to recognize. In math, we use radians instead of degrees. For one big reason, because in calculus, we need radians in order to do the math. Radians are a natural way of defining the angle measure, whereas degrees are something we made up so that we can actually measure things in nice fractions. And so 360 has a lot of nice divisors. That's why we use degrees. But radians are actually a real interpretation of the angle. And so radians, one really nice thing is that a radian can be thought of as just a number. And so when we are using radians, we're making functions which go from the real numbers to the real numbers. We can graph that. Trig functions are periodic. And so that's another thing to note. Periodic means that they repeat themselves after a fixed interval. And so in the case of all trig functions, if you are at f of x plus 2 pi, that's the same as f of x. If you go 2 pi to the left, 2 pi to the right, you're getting the same y values out. For tangent and cotangent, you don't even have to go 2 pi, you can just go pi, and you're going to get the exact same value out of it. This means that to understand the behavior of the entire graph, we only really need to understand a small portion of it. And so let's understand some small portions of graphs. Here is sine and cosine. And so sine is in red and cosine is in blue. And so note that sine starts at 0, 0 and cosine starts at 0, 1. But then they just oscillate. And so they're going to repeat themselves every 2 pi, but they're going to go down and up and down and up and create this wave-like pattern all the way throughout. We use these to model a lot of things. Anything that is rotating, anything that is oscillating, any curved orbits. Sine and cosine, they are some of the fundamental motions of the universe. And so we see them a lot. Tangent is a little bit messier. We can think of it as sine divided by cosine. And so tangents and cotangents are often used when modeling position. Since sine is the y component and cosine is the x component, the tangent is the sine divided by the cosine, which is y over x. We can use this to represent rise over run, which can tell us the slope. And sometimes we need to go the other direction. And so that's when we would use the cotangent. So here's the graph of the cotangent function. Again, this would be cosine divided by sine. Our secant graph is a little bit weirder. It is the reciprocal of the cosine. And so usually we will draw the cosine graph in and use that to figure out what the secant graph looks like. Cosecant, similar idea, but now it's the reciprocal of sine. Now, when we think of sine and cosine, we can transform them in a lot of different ways. To begin with, we can use values, real values, in order to shift and manipulate them, just like we did all of the other functions. But because they have a wave-like structure, it's real easy to see how they are being compressed. And so in this example here, this is 2 sine of 3 pi over 2 times x minus 3 plus 4. And so I've shifted the graph up to here as its new starting point, and then I've compressed it and stretched it in a number of different ways. We can also use functions, though. And so in this case, I've used a function as a multiplier. This is the function x squared times sine of 10x. And you can see what this has done is this has affected the amplitude of the sine wave. And so now the amplitude of the sine wave is the x squared value. We can also add functions to sine curves. And so in this case, we have sine of 10x plus the square root of x. What this has done is this has shifted up how this function is going to be oscillating. And so instead of oscillating between -1 and 1, it's going to be oscillating between square root of x plus 1 and square root of x minus 1. We can also do compositions of functions with sine. In this case, I've done a composition of sine of x with 2 to the x. And so when you're plugging 2 to the x into a sine wave, it ends up making it so that there's hardly any curves on the left side. And then on the right side, it begins to oscillate very, very quickly. Whenever we want to show how how sine curves or waves are oscillating in different ways, we can use this type of compression. As for a general model for oscillating functions, we can take these 3 things into consideration. We have a function for the amplitude, we have a function for however we're going to be modifying the inside of it, and then we have the vertical shift. And so this is going to give us a general shape for any trigonometric or any sine curve. So if we ever want to have something which has a wave-like structure, we can use this type of formula to generate a wave structure. One last big topic is going to be inverse trigonometric functions. We must undo what was done. Now, the biggest challenge with inverse functions is they are not one-to-one. And so when we think of the trig functions, none of them are one-to-one. And so that means that when we are trying to find the inverse, we are going to take some region which makes sense and then try and find the inverse of that. When I say find the inverse, we're really just defining these functions as the inverse. And so we'll go through them fairly quickly. Here is our inverse sine function. Here is our inverse cosine function. Here is our inverse tangent. Here is our inverse cotangent. Here's our inverse secant and our inverse cosecant. Final thoughts. Well, there's a lot to discuss related to trigonometry functions and their graphs. If you've never done trigonometry before, we just introduced 12 new functions, the 6 trig functions and the 6 inverse trig functions. There's a reason trigonometry is often treated as its own course. You might be able to cover the entire contents of trigonometry fairly quickly, but really, if you want to go in depth, it's easy to go into a lot of depth for trig. In combination with the functions of algebra, we will now have a full set of functions with which to explore the fundamentals of calculus. This is it, really. When we think about the algebraic functions and the trigonometric functions, you put them together and you have a total set of functions. And we'll see why that is once we start playing with calculus. With that, I'll let you get to work exploring where you find trigonometry in the real world. Good luck, folks.